This is the AN-602, more famously known as the Tsar Bomba, the most powerful nuclear device ever detonated in human history. Developed by Soviet scientists during the intense rivalry of the Cold War, the Tsar Bomba produced a staggering explosive power of 50 megatons of TNT, a yield unmatched by any nuclear weapon ever tested. In this video, we will explore the Tsar Bomba in detail, examining its design, its purpose, and whether such an enormous weapon could realistically be used in warfare or alter the balance of the global arms race. Our focus will be on the bomb's historic test, from the moment it was loaded onto its aircraft carrier, through its release and detonation, and finally the dramatic aftermath. My name is David Webb, and this is Blue Paw Print. The Tsar Bomba was a massive air-dropped thermonuclear weapon. The bomb measured roughly 6.9 feet in diameter and 26 feet in length, comparable to the length of a classic London double-decker bus. Its total weight was around 54,000 pounds. The exterior casing was constructed from steel, internally lined with beryllium. Beneath this layer was a synthetic thermal insulation material designed to keep the highly sensitive nuclear components and explosives within a stable temperature range. At the front of the bomb sat the control module, protected within its own reinforced casing. This system connected to radio rangefinder antennas and barometric sensors, which were responsible for determining the exact altitude for detonation. At the rear, the bomb featured 3 fixed fins that helped stabilize it aerodynamically during its descent. Behind these fins was a compartment containing a multi-stage parachute deployment system. To understand how the Tsar Bomba functioned, we must first look at how it was delivered. The aircraft chosen to carry the Tsar Bomba was the Tupolev Tu-95V, a heavily modified version of the Soviet Tu-95 strategic bomber, a large 4-engine turboprop aircraft. To accommodate the enormous bomb, the aircraft required major structural changes. The bomb bay was expanded to 5.8 feet in width and 23.45 feet in length. A specialized beam-type mounting rack was installed directly into the aircraft's structural support beams to secure the weapon. To make space, 2 internal fuel tanks were removed and a structural bulkhead was repositioned. The defensive machine guns in the tail turret were removed, and in their place, engineers installed instrumentation probes designed to record the thermal radiation and shock wave produced by the explosion. Additionally, the aircraft's exterior was coated with a special white reflective paint intended to reflect the intense heat and radiation from the blast. Even with these modifications, the Tsar Bomba was so large that it had to be carried partially outside the bomb bay. Once the bomb was carefully installed and ground inspections were completed, the Tu-95V received authorization for takeoff. The aircraft departed from Olenya Air Base, located on Russia's Kola Peninsula, approximately 92 kilometers south of Murmansk. After takeoff, the bomber climbed to an altitude of roughly 6 miles and began its journey toward the designated test area. The test site was officially known as State Test Site Number 6, located on Novaya Zemlya, a remote Arctic archipelago in northern Russia. The testing range covered an enormous area, more than 21,000 square miles of land and 14,500 square miles of surrounding water. The specific detonation zone, known as Zone S, was located about 9 miles north of Michushika Bay. The nearest inhabited settlement, Severny, was roughly 34 miles away. Although this distance was believed to be safe, the population had already been evacuated. On October 30, 1961, at 11:32 a.m., the Tu-95V reached the target zone and released the bomb. Immediately after the release, the parachute system deployed. The parachute assembly weighed nearly 4,000 pounds and contained 9 separate parachutes. The deployment sequence began with a small drogue parachute measuring 5.4 square feet, which pulled out a larger 54 square foot parachute. Following this were 3 parachutes of 65 square feet each, and then 3 more parachutes, each measuring 430 square feet. Finally, the enormous main parachute canopy deployed. With a surface area exceeding 17,000 square feet, it was approximately 3 times larger than the wings of a Boeing 747, making it one of the largest single parachutes ever used. The parachute slowed the bomb's descent for 188 seconds, giving the bomber crew enough time to escape to a distance of roughly 28 miles before detonation. The Tsar Bomba was designed to detonate at an altitude of about 13,000 feet above the ground. This height was carefully calculated by Soviet scientists to maximize the blast's destructive power while minimizing radioactive fallout. The bomb's radio altimeter sent signals toward the ground and measured the time it took for the reflection to return. These readings were cross-checked with barometric pressure sensors. Once both systems confirmed the correct altitude, the weapon's safety mechanisms disengaged. The bomb's first stage was a fission device consisting of 2 plutonium spheres located in the forward and rear sections of the bomb. Each plutonium core was surrounded by a shell of high-performance explosives, detonators, and a beryllium reflector casing. When triggered, an electrical system discharged high voltage into gas-filled spark gaps, firing all detonators within 0.1 microseconds of each other. The explosives compressed the plutonium cores inward. Once compressed, the plutonium became supercritical, initiating a nuclear chain reaction. Neutrons split plutonium atoms into smaller nuclei, releasing enormous energy and additional neutrons, which continued the chain reaction. The surrounding beryllium reflector helped bounce neutrons back into the core, greatly increasing efficiency. This reaction produced temperatures reaching 100 million degrees Celsius, several times hotter than the core of the Sun. The intense burst of X-rays and gamma radiation from this stage triggered the bomb's second stage. The second stage contained a lead outer casing, a layer of lithium deuteride, and a central plutonium rod. Neutrons from the primary explosion caused the plutonium rod to become supercritical, producing additional neutrons. The lithium deuteride absorbed these neutrons and produced tritium, a radioactive form of hydrogen. Under extreme heat and pressure, deuterium and tritium nuclei fused, forming helium and releasing enormous amounts of energy, the defining process of a thermonuclear explosion. The lead casing acted as a tamper, briefly containing the materials so the fusion reaction could develop fully. Originally, the bomb was designed with a depleted uranium casing, which would have increased the explosive yield to 100 megatons. However, lead engineer Andrei Sakharov ordered the uranium replaced with lead for the test. This reduced the bomb's yield to 50 megatons, but also decreased radioactive fallout by nearly 97%, making it the cleanest high-yield nuclear explosion ever produced. The entire chain of nuclear reactions lasted less than a microsecond. The detonation began with an intense flash of light, described by witnesses as brighter than the midday sun. The flash lasted for more than a minute. Soon after, a massive fireball formed, expanding rapidly to nearly 5 miles in diameter, large enough to engulf an entire city like downtown Los Angeles. The fireball expanded so close to the ground that only the shock wave reflecting off the surface prevented it from touching the earth. Had it reached the ground, radioactive fallout would have been far more severe. The explosion then produced an enormous mushroom cloud, rising between 40 and 42 miles high, nearly 7 times taller than Mount Everest and extending well above the stratosphere. The top of the cloud spread to roughly 59 miles across, while the base reached about 25 miles in diameter. The blast also produced seismic activity equivalent to a magnitude 5.0 earthquake. Even at a distance of over 60 miles, the Tu-95V bomber was violently shaken by the shockwave and temporarily lost altitude before the crew regained control. The aircraft eventually landed safely, although its protective white coating showed signs of scorching. Effects on the ground. On the island below, the rocky terrain was reportedly flattened and melted, forming what observers described as a 5-kilometer-wide blackened area of fused earth. The settlement of Severny, located 34 miles away, was completely destroyed by the blast. The shockwave was powerful enough to be felt 560 miles away, including in Norway and Finland. Legacy and impact. Despite its immense power, the Tsar Bomba was impractical as a weapon of war. Its enormous size and weight made it difficult to deploy, and its destructive power far exceeded most military requirements. Instead, it served primarily as a political demonstration of technological power during the Cold War. At the same time, the test reminded the world of the catastrophic potential of nuclear weapons. Just 2 years later, in 1963, the Partial Nuclear Test Ban Treaty was signed, banning nuclear tests in the atmosphere, underwater, and in space. In many ways, the Tsar Bomba helped push both superpowers toward nuclear restraint rather than unlimited escalation. Conclusion. The Tsar Bomba remains a unique chapter in the history of nuclear weapons, a symbol of both scientific achievement and the terrifying destructive potential humanity possesses. If you're interested in the origins of long-range missile technology, be sure to watch our video on the V-2 rocket, the first mass-produced ballistic missile. Researching and analyzing a weapon as complex as the Tsar Bomba requires significant effort, and much of its design remains classified even today. If you notice any inaccuracies, feel free to share them in the comments. Thank you for watching.